Hello physicists, today we're going to build on our knowledge about electric fields, give some examples. Now you'll remember from Friday's video that electric fields cause a force on a particle that's at a position. So the electric field is doing the pushing pulling, the charge has units of Coulomb, the electric field's strength has units of newtons per Coulomb, so that gives us our electrical force. You'll also remember from our last video that the way that this differs from our gravitational field is that because Q can be either positive or negative, if I have a positive charge, my object is going to be accelerated in the direction of the electric field. If I have a negative charge, it's going to have a force on it in the opposite direction of the electric field. So, for instance, the question might arise, what is the evidence that I have that a particle is actually experiencing an electric force? Well, one obvious way that you can tell that an object is experiencing a force is that it's accelerating. We have to use our F equals ma. So here's a particular example that says, what is the magnitude of an electron's acceleration in a uniform electric field with a big magnitude, 1.4 times 10 to the 6 newtons per Coulomb? And then it asks, how long would it take to reach 1/10 of the speed of light, and how far would it travel in that time? Well, first off, we're asking the question, what is the magnitude of an electron's acceleration? Okay, well, I can use here that the size of the electric force is going to be Q times E. So in this case, if I have an electron, the magnitude of the force is just going to be that fundamental charge, that 1.602 times 10 to the minus 19th coulombs. And the E, the size of the E they give me. And on the other hand, if that electric force is the only force that's acting on a particle, I can write F equals ma and use my Newton's second law. And then I'm just going to set these two equal to each other and get F E times E, the charge times the electric field, equals m times A. And then if I want to solve for A, it's just going to be the force divided by the mass. So in this case, the acceleration would be my 1.602 times 10 to the minus 19th coulombs. And my electric field strength would be my 1.40 times 10 to the 6th newtons per Coulomb. And then my mass, I would have to use the mass on the electron, that 9.109 times 10 to the minus 31 kilograms. Okay, so in this case, that would be 1.602 times 1.40 divided by 9.109 times 10 to the minus 19th times 10 to the 6th times over 10 to the minus 31, so that's going to be times 10 to the 31. And if I go and plug all those numbers in, I'm going to get a big acceleration, 2.46 times 10 to the 17th meters per second squared. Okay, and then of course, if you wanted to go farther than that, you could also go ahead and find the amount of time it takes by saying, okay, your final speed is 1/10 of the speed of light, so that would be 3 times 10 to the 8th divided by 10 equals the acceleration times the time, so solve for t. That would be part B. So this is part A. And then part C, you could go ahead and use, for instance, how far would it travel? You could use the time that you find there and go 1/2 a t squared. And then the initial velocity would be 0, and the initial position would be 0, and that could give you your answer. Okay, if you're curious on those, you can go ahead and stick in numbers. But my main point for this example is just to say, if you want to know that an object has a force on it, you know that you can say if it has an acceleration. Now, if you want to go ahead and see another qualitative example of this, here's another question from the book. It says, what if we have 5 protons that are launched into a uniform electric field? The magnitude and direction of the launch velocities are indicated. Rank the protons according to the magnitude of their accelerations due to the field, greatest first. Now this is sort of a trick question because if you notice, in the last problem, we found the acceleration of an object in the field. We did not specify the initial velocity. We assumed that it was 0 meters per second. But how would that change things? It turns out it doesn't change it at all for this question because the force that's acting on them is still just going to be Q times E. Q in this case would be the electron, the fundamental charge, positive for a proton, negative for an electron. And if we wanted to find the acceleration, we would set this equal to ma, so the mass of the proton times the acceleration of the proton equals E times E, just like before. Okay, so in this case, the acceleration would just be in the direction of the electric field. You'd have a factor of E over m. But the fact is that because these all have the same charge, they all have the same mass, they're all going to have the same acceleration. So that's a little bit of a confusing point. Don't get tricked. Okay, so today we're going to go ahead and move ourselves toward applications of electric fields. So I said this briefly in the video on Friday, but I'm going to repeat it again. If we compare these two forms, let's say that we have an object Q1 that's pushing on another charged object Q2. Okay? In this case, the force of object 1 pushing on object 2 would be equal to K Q1 Q2 over R squared. Remember, the K is just that 1 over 4 pi epsilon naught, around 9 to the 9 Newton meters squared over Coulomb squared. That force, in our new way of thinking about it, we think about the force as being caused by the electric field that's hanging out in that region, acting on this Q. So that force from particle 1 is going to equal the Q on particle 2 times the electric field from particle 1. So now I'm going to set these two equal to each other and then cancel out the Q2s. And when you do that, what you find is your E is just KQ over R squared. And so that gives you my your electric field contribution from a charge. For all of our positive charges, the electric field vector contribution is pointing out because it tells us the direction that a plus charge gets pushed on. If it were towards a minus charge, it would be pointing in. And this is because our convention is just that the electric field tells us the direction of the force on a positive particle. And we can always find the direction of on a negatively charged particle just by reversing it. So here's a simple example. Let's say that you have a nucleus of a plutonium-239 atom with 94 protons. Plutonium is famously radioactive, but the idea here is that the nucleus has both protons and neutrons, and if you have a lot more neutrons than protons, that causes instability. And here are the 94 protons. That gives us our Q is 94 times E, the fundamental charge. It says that the nucleus is a sphere with radius 6.64 femtometers, so there's your R equals 6.64 times 10 to the minus 15th meters. And with the charge of the protons uniformly spread through the sphere. At the surface of the nucleus, what is the magnitude and direction of the electric field produced by the protons? So, it turns out that we're actually using one of the shell theorems that I mentioned on a previous video that says if you have all of your charge uniformly spread out about a central point, you can treat it all as being located at the center, sort of the same way that we had a center of mass with respect to gravity. So in this case, we're going to find our electric field is this number. So that's my 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. So that's this number. And then I have my Q, which is going to be 94E. So that's going to be 94 times 1 point. Let's make sure I get this right. 1.602 times 10 to the minus 19th coulombs. And then we're going to divide that by r squared. So that's this number squared. 6.64 times 10 to the minus 15th meters squared. Okay, and of course I have already encouraged the route towards sticking stuff in your calculator of keeping the easy numbers out front, times 1.602 divided by 6.64 times 6.64 times 10 to the 9th, 10 to the 19th minus 19th, 10 to the minus 15th. And the meters squared down here cancels out the meters squared up there. One of the coulombs is canceled out there. So we have the right units of newtons per coulomb. And you can stick in the numbers and find that we get 3.07 times 10 to the 21st newtons per coulomb. Okay, and of course, because it's positive charge, it's pointing outward. Now, the reason why this is a little complicated is that when we have more than one charge, each charge that's in the vicinity of a region of space is applying a vector contribution to that net electric field. And so you've got to add together all of those different contributions to get the total electric field at a point in space. So here's just something to give us an example that we can try out and see how it works. So here we have 4 situations in which 4 charged particles are evenly spaced to the left and right of a central point. The charge values are indicated. It says rank the situations according to the magnitude of the net electric field at the central point, greatest first. So this is sort of a qualitative problem, and the way that we can know that we're going to get it right is that things that are closer to this point, we're looking at this point to find the electric field contribution right there. Things that are closer are going to have a bigger contribution than things that are farther away. And things that have a bigger charge would have a bigger contribution, but all of these have the same charge. So that simplifies our problem somewhat. Now, just to zoom in a little bit, this minus E and minus E, since those are both on either side of it, they are going to cancel out because one is going to, this particle is going to have an electric field contribution pointing to the left. This particle is going to have a contribution that's pointing to the right, and they cancel out. And ditto for these. Okay, so those also maintain the equilibrium. And so here, our electric field is just 0. Okay, so that is an easy one. On the other hand, if we say 1, 2, 3, 4 are our different electric field contributions for this, well, for particle 1, it's far away from the center, so we expect the electric field to be pointing out, so there would be my E1. My E2 is also going to be pointing away because it's positive, but it's going to be bigger because the particle is closer. So there's my E2. And then I also am going to have my E3, which is going to be big because it's close. Same magnitude as E2. And then my E4, which is going to have the same magnitude as E1. And if I want to have all 4 of those, I have to add them up like vectors. So I'm going to do that off to the side here. I would have my E1, and then I would have my E2, and E3, and E4. So there is my net electric field, pretty big as we're going to get. Okay, now same idea here. These ones are going to, effectively their contributions are going to cancel out because they're going to be in opposite directions. And then right here, I'm going to have my, if I call this 1 and 4 again, I would have my E1 pointing into the minus. So there's my E1, it's small, and my E4 is also going to be pointing in the same direction, but because it's pointing out from the positive, so there's your E4. And so this is going to be your E4 and your E1. Okay, so there's your net electric field, adding them as vectors. Okay, and in this case, these outer ones cancel because they're same charge, same distance. Their contributions negate one another. And then over here, the forces are going to be bigger. So on my 2 and my 3, I have my E2 pointing toward into the particle, and then my electric field contribution from 3 is going to be pointing away. So here I would have my E2 and my E3. Okay, so my E total. And the thing to be aware of is that electric field it's attached at this point in space. So we can't really just move it around. But it's pretty easy to see here that my 2 is going to be bigger than my 3 is going to be bigger. Whoops. 2 is going to be bigger than my 4, which is going to be bigger than 3, which is going to be bigger than 1. Okay? So that's how we think our way through. Now we can also think our way through even more complicated situations. Like consider this one here. It says, consider we have 2 negatively charged objects that are located on the x-axis. So right here and right there. And it says, they're equally, we want to consider the electric field at this point P1. Now, I can already think my way through this because let's call this a particle 2, or particle 3 and particle 4, just so I don't step on any toes, 3 and 4. My electric field from particle 3 is going to be pointing toward 3 because it's negative, and the electric field from particle 4 is going to be pointing toward 4. And I notice that there's a mirror symmetry here where the x components from E3 and E4 cancel out. Okay, and then when I add those together, it's just going to be the x component of this one plus the x component of that one. On the other hand, it says, how will that electric field change if a third object with charge plus q is placed at point P2? Okay, so plus q is, if I put that up here, what happens? Well, let's call that particle 2. That's going to have an electric field pointing down. It's going to be pointing out, and it's going to decrease this electric field slightly, but not as much as either one of these, because this is in fact farther away. So it's farther away, so it's not going to decrease it by half. It's going to be more like 25%. Okay, so that's the only one that's possibly right on this one. Now, it does seem to me like it's useful to sort of write this one out more explicitly. Okay, how would we write this in terms of all of the math? Well, okay, so here's our, if we put a plus q there, this would be our, here's my particle, let me make sure I'm going to keep that consistent, 3 and 4. So there would be my E3, here would be my E4. And in the first case, you just have E3. Now, if you're looking at this, the magnitude of that has to be KQ over R squared. Now, what is the R? Well, if I have a triangle like this, it's going to be R, R, and this is going to be square root of 2R. And if I square that now, because remember my electric field is going to be K, which is 1 over 4 pi epsilon naught, Q over R squared. So for my E3, this would be K, Q over square root of 2R, and then square that, so that would be 2R. And then if I'm looking at this angle is 45 degrees. That angle is also 45 degrees. So I can split this into an x and y component. My x component would be in the minus y, or the minus x direction for E3, so that'd be minus sine of, minus cosine of 45, the way that I've written it. Turns out it doesn't matter for this case. And then plus sine of 45. So that's my E3 in my x and y direction. And then my E4, same magnitude, because it's the same distance away, same charge, so KQ over 2R. And then the x component is in the plus x direction, the y component is in the plus y direction, so this would be plus cosine of 45 degrees plus sine of 45 degrees. Okay, so E3 plus E4 is equal to, and this is just going to be square root of 2 over 2. Well, this is going to be 0. This is going to be KQ over 2R. And this is going to be 0. And this is going to be 2 times square root of 2 over 2. So that's going to be just root 2 there. Okay, and then I also just have my electric field pointing out from my Q2, so my E2. And so in my other case, it would be KQ over 2R squared, because this total distance is 2R, R plus R is 2R, and then you square that, you get 4R squared. Whoops, I left off my squared, squared, squared. This should be 4R squared. And this is not going to be, it's going to be pointing entirely in the minus y direction, so 0, minus 1. Okay, so in this case, if I wanted to have my E2 plus E3 plus E4, it would be this stuff plus that. Okay, so it would be 0, comma, and then it would be all of that. So square root of 2 over 2 kq over 2r squared. Oops. I'm writing that badly. So square root of 2 over 2 times kq over r squared. And this would be minus 1 over 4 kq over r squared. Okay, and so if you wanted to compare these two, you could. All right. So it's a little bit of a messy problem once you start putting in numbers. It cleans up, but I think that's far enough. Now the other thing I just want to bring up in this video is the idea of different types of charge densities. So we're going to be considering the electric field contributions of various types of charge distributions from a line of charge. And for that, we usually use the symbol lambda. It has units of coulombs per meter. We are also going to be considering surface densities. That's where I have a bunch of charge spread over a 2D surface. In that case, we usually use the sigma, and that's coulombs per meters squared. And we also can have a volume density where we have coulombs over meters cubed. So that's my charge spread out over a volume. Now, I did give a homework that has to do with this, and I just want you to practice. So in each one of these cases, it's having you calculate line densities, surface densities, and volume densities. It's having you use the same charge in each case. So minus 300 E, remember E is that 1.602 times 10 to the minus 19th coulombs. In the first case, it says this charge is uniformly distributed along a circular arc of radius 4 centimeters, which subtends an angle of 40 degrees. So you have a circle. They want you to find what is this length if this is 40 degrees. So you would take 2 pi r. They give you the r, and then take 40 over 360 to get that particular length. And then your line density would just be, so you'd find that S, how long is that? And then you take your Q over S. On the other hand, in the second part of the problem, it says a charge is uniformly distributed over one face of a circular disk. Well, if you have a circular disk and you're looking for the area of a circle is just pi r squared. And your sigma, your surface density, is going to be the amount of charge that you have, which they give you, over the area. So there's your part A, there's the part B that you're going to work on. Part C says, what if you take that area and spread it out over the surface of a sphere? Well, famously, a sphere has a surface area that's just the surface that you're going to paint. The surface area turns out to be 4 times bigger than the area of the shadow of it. So it's 4 pi r squared. And then if you wanted to find that, you're going to have to take your Q over the surface area. So in that case, you have this charge spread out over the surface of the sphere, but not on the inside. And then for part D, it says, well, what if you took all of the charge and instead of just having it spread on the surface. What if you spread it out through the whole thing? And in that case, you'd have to use the volume of the sphere, 4/3 pi r cubed. And in that case, the density, the charge density would be that Q spread out over the volume. Okay, so I just gave you that problem to get you comfortable thinking about what are the units on each one of these types of quantities. Now, in your book, they give you a couple of different interesting examples where they calculate the electric field from various geometries. So here's, for instance, if you have a ring of charge, what I want you to think about is that you can split that ring of charge into differential quantities. And the reason why it's a little bit of a slick problem is that the component of the electric field, that if we're just looking about at the electric field along the axis, those x components, or in the xy plane, will all cancel out because the charges on one side of the ring are canceled out by charges on the other side of the ring. So what it turns out is that we only have to take the electric field contributions that are going to be along the axis. Okay, so that's what our cosine of theta does for us. And we can now go ahead and integrate all of the contributions on the on-axis contributions from each little piece of charge and integrate all the way around the circle. And once we do that, we find our result. And what's interesting about this is that once z is way bigger than r, this just looks like a point charge. So if z is much bigger than r, my r can effectively go away, and this just becomes e. Whoops. Okay, so if I let my r be 0 in this expression, this is e equals 1 over 4 pi epsilon naught, and then I get z cubed to the 3/2 power of z squared, and so that's just basically z cubed, but I have z up there, so this is basically just 1 over z squared. So that looks just like a point charge, okay? And then what happens if z is much less than r? Okay, so if I let z get really small here and really small there, it effectively goes to e equals 0. So that's interesting, and there's also an obvious physical explanation for that. If I put this my particle right in the middle of the ring, all of the charges pulling one way are going to be counterbalanced by forces pulling the other. Okay, so there are more examples like this in your book. For instance, disk of radius r. The most significant one of these is going to be that of the dipole, which has a field that dies off as 1 over r cubed. And this is basically if you have a plus and a minus charge that are separated by some small distance. And in our next video, we'll talk about how torques on dipoles allow things like microwaves, for instance, to heat your food up. But that's enough for today. So what have we learned? Electric forces on charged particles cause them to accelerate. Okay, so if you have a force and an acceleration, or a force and a mass, we can figure out what the acceleration is. So that's what we did first. The next thing we did, we talked about how point charges provide vector contributions, pointing out from positive charges into negative charges, and you can add up the contributions as vectors to find the net electric field at a position in space. And then our last thing that we did, we talked about how electric fields surrounding a general charge distribution can be calculated as in the case of the ring. Okay, so stay tuned. We'll be back in another 2 days.